I need that. I want to see to just start to know the work will come much. We just need to be fast so that we can do that at our manner. And then please example. I agree with question 1. No, we are doing it. Now we will do it. Come on, right? You need to someone. Okay. You know, we have to go and get it so that it's balanced everybody. Because the non-medical students are done with most of the graph. So we'll try to do Workbook fast. Then we'll start the practical one. So please give me question 31.
It's coming to operate with some table.
Okay, come table. Of resistance centimeter, yes?
Rotate at an angular acceleration.
Rotate
at an angular acceleration.
Angular
acceleration. Don't listen of 4 rads per second.
Of 4 rads
per second. At the end of 3 seconds.
At the end
of 3 seconds.
Is that all? Okay, please, let's not come to class yesterday. We did this. I know it's more of the non-medical students that came to class yesterday. So please, solution. Please, let's develop. Hello. This is class for learning, not lectures. This is class for teaching and learning. So please don't come and come with your. So please, remember yesterday we said that once you see acceleration, that the first thing we need to think of is the questions of uniform circular motion. Is it not true?
Yes.
And I said that if you're giving acceleration, like they did not mention the initial acceleration, take the initial velocity, take the initial velocity. Now that's it. For that equation of because the W naught plus yes. So I can now say this is radius of they give me some type of radius, so they have nothing to do with radius. Then my initial velocity will go 0. Then plus 12. Very simple. So actually they asked me to find any other thing like yesterday, so where they asked me to find centripetal acceleration. That's where we have come and start doing this W all over this N. I think that is V squared. But since they didn't ask me, I'll give you what they asked me to find. That is the answer. So 12 grams per second. I am giving question 32. Can I get it? 32, shall we?
Yes.
We have to be fast. Why is that?
Of my show by graph.
About 0.05 so rotating about vertical axis, yes. 10 centimeters from it, yes.
If the body completes the revolution,
The body
completes the revolution, every 3 seconds.
Please pay attention So these only two people that is in this class. What does it just waiting for us to stress? How many of finish Okay, frequency of rotation. So we're just looking at frequency. Can I clean this now?
Yes.
No, this side. I want to clean this. You know that when the board is filled up. So I like if you do this, you pay attention to it. So please now, a second point particle is 0.0. But we don't use 0.05 grams. Is it not? Yeah. So we do 0.05 gram times 1 kg is to how many grams? Gram cancel gram. I want you for me, you have what? Is it? Yes, I should be correct. Yeah, so that is for my kg. So I'm converting to the SI unit. Now, what did they ask me to find? Moment of inertia. Now, remember that moment of inertia is given by I equals to m times squared. But how do you mind that as we progress, there are different bases? So this now, when we say moment of inertia, we know that it talks about mass and rotating axis, the orientation. But we'll still see different results. Just to see. 5 times L is equal minus 5 times 0.1. What about it for me? What the other? 5 times L is equal. Okay, so yes. I am 5 times L is equal. And you need to be in kilogram. Yes, meters square. I am giving that 3. Can I clean this one now? Yes. Yes, remember frequency is given revolution per second. Is it not true? Yes. That means how many revolutions do you give us? Over 10. Is it not true? So 2 grams. Which is 0 points. This is my what we did yesterday.
Yes.
This is not medical students will show you for this class. The medical students, because I know everything that was there, some medical students that was there yesterday. Why some was waiting for biscuit and coke. So why is it? Yes. Okay, is it water? Okay. Why is it refreshment? Please, why is it question 3? I can drink. This thing is on your mind now. It's just because of your workbook. I'm just writing it because some people are not there. My name is on your mind now. I am what now? There's what? The expression for the expression about the point passing through. 1n is what? I have paid attention. Some of you are good with copy. You go online, you copy. I am doing pay attention. Let's get how to copy and something. What is this? 33. We need to be fast so that we do 50 and 10 moves to another thing. I should wait. We need to be fast. We need to be very fast. Is it your number? When I see, I know that first of all, density. What's the formula for density? Mass over volume. So I know that density, I can represent density. Yeah, I can represent density with mass over volume, which is meter cube. Is it not true? But please, when we are talking about a bar of length, we say that it's in just one dimension. So we are not going to be using and we just use L. Are you saying it? Yes. So please, for a one-dimension body, just a dimensional body, the density is simply M over L. Why for a three-dimensional body, which is the normal things you do, the density is L raised to power M. So we have M raised to power all over L raised to power. So in this case, we're talking about something in one dimension, now you're back. We're using L. Now what I will say is just applying our mathematics knowledge, which is BM and BL. Is this thing confusing?
Yes.
Do you know what this thing means? Change in mass over change in length. That's what it means. Change in mass over change in length. So for that reason, I will say if that be the case, let's say I want to make change in mass, solid or formula, what will I have? I have change in mass to equals to density times change in L. Is it not true? But since I know that moment of inertia is what they're asking me, I will place this L with R. Which means that I can replace this with R. Are they not the same units? M and R, they are in the same units, which is meter. Because I know some of you are very close. So I will replace it because I'm dealing with inertia. So normally I can leave it. So I put this to the R. I put this to the R. Do you know why? Because I know that when I started class with you, I told you one time that moment of inertia is given by integral of R squared. Then N. When we started class, I told you that if I have, for example, anything like, let's say, velocity equals to change in displacement over change in time. If you say cross multiply, this is the same as saying V dt equals to ds. Is it not true? Now, if you want to make ds solid of formula, d will cross the equality sign and turn to integral. So it will have the integral of v with respect to time is equals to s. So that is the same case with anytime you see an equation that has product of something, it simply means that one is with respect to the other. So that is what we have here. So that is why I changed this L to R. So that by the time I carry this value that I'm seeing now, the M is equals to density and the R. Are you understanding? I remember that we said that density for a one-dimensional body is equals to M over N. Is it not true? Then when we use the integration, we got it to this. This thing we are seeing here is the same thing with this thing. What we know, just that we keep changing. So let's just have this thing so you don't get confused. So what we have is to say, anytime I see the N, the first thing will be so that I will have. This is how you get for every of the body that I have. So this will have to be as saying integral of R squared, bring B, bring R to replace this. Are you seeing it? So the meaning of yeah, see now, shall we make change in mass subject of the formula so that we now have P, that is, this stands for density, I don't want to write density, we now have P times the R. So I now said that since I know that the equation of that moment of inertia has integral of R squared with respect to Bn, replace Bn with the value we have here. That's what I've done here. So that I can be able, and why am I doing this? Because I know that there's R that I will get for in moment of inertia. So by the time I replace this value now, you see that what I will have doing is simply to integrate the R squared that we are using in this equation with respect to this R. Somebody will say, what of the density? Density is a constant here because I have R and I have R. This becomes a constant. I just put it away. So that this can be sent as I is equals to bring out my constant. In integration, you don't have to bring out your constant. So that I'll now have integral of r squared with respect to r. Or you say changing r squared, integrating r squared by changing the r. And this is the r I'm going to be changing. So this thing is now the same thing as saying integral says add 1 to the power. Divide by the new power. Is it not true? So even without doing all these steps that we're doing, anytime you want to find moment of inertia about an axis or at the center, this thing becomes a formula that you now substitute. So after learning this, just know that if you just want to know this, without even stressing yourself doing this thing, it's simply the same as saying, if I come and say, I integrate in moment of inertia is simply integral of r cubed all over cubed with respect to r. Very simple. So anytime I'm giving any equation or anything about moment of inertia that has to do with an end or axis, this is the formula I need. Because now I can integrate this. I remember that there is P here, sorry. Yeah, this is the formula I need. So you need to know this formula. So that we can now go ahead and solve it, simplify it further because it's not finished. So if I simplify further, somebody wants to ask me how did you do this? Please, this is simply integration. Add 1 to the power, divide by the new power. That's just it. Okay, ask me more. Why did I change from here to R? Okay, do you know that this thing, do you know that this moment of inertia is the same as saying, moment of inertia is the same as saying ml squared. Hello? Do you know that moment of inertia is the same as ml squared? Okay, no. So if I am using ml squared, if I'm using ml squared, I will have to change it to R. So that I changed it to R because we are used to that pattern of using R squared for the moment of inertia. So but if I don't want to change it, I could have said, since this one I come and make the formula to the integral of L squared with respect to M, I won't have to change this R. This L that's supposed to be here to R. So if we want to use whichever way, just know that the moment of inertia is this, and if you're using this, you don't have to change your code from that density. But if you want to use R squared, you have to change this. That's how we use it. I remember that we said that moments of inertia simply talks about a body of mass that is rotating. And when that body is rotating, you don't just call it mass, you call it inertia. And that means you are taking note of it going vertically, it's going this way, it's going this way, it's going this way. I know that area is given by bigger than squared. So those axes, the first dimension vertical, horizontal, that's what we are checking. So you can use that length and replace it with R. So if that be the case, you see we don't have any issue. So what I can do here is to simply integrate this. I will say that this thing is going to be now looking at the question. If this becomes my bar of length, watch. If this becomes my bar of length, and they say passing a point through one end, look at this, they say inertia of a bar of length M and mass M about a point passing through one end. See what this thing means, please. Watch what this thing means. Let's say this is the one end that ball is passing through. Let's say I have a circle like this. Let's say I have a ball. Or let's say I have a bar. And then let this be the mass M. What this thing means is that as this thing now is rotating here, as it's rotating here or passing through these points, because we're talking about moments of inertia, it means that the body is rotating. Notice that it is not happening this side. You see now, it is different from, let's say, for example, I have this, for example, and I have a body of mass, let's say, in between. Let's say I have this in between. You see that in this case, this thing is being shared. You see now two sides. So it's going to be going in between. So in this case, we'll simply say that this length will be divided by 2. This length will be divided by 2. And we'll now check the x-axis. Remember that moments, we always think of that our clockwise and anti-clockwise. So I will now say this is the negative x, this is the positive x. In the other things I've been teaching you about angular motion, in as much as we don't want to talk about it because we know that once we do this one equals to this, we don't want to put that signs. But once you're talking about angular motion, you need to always know that the minute you are moving this way, if this is my x coordinates and y coordinates, notice that if I start here, this is 0, should be? This is 90, right? 180. 270, 360. Notice that if I'm going this way, I'm going the way that respects this coordinates. That is from 0 going towards 90, going to. So this is considered positive. So whenever you are going counterclockwise, notice that this is counterclockwise. In rotational motion, once you are going counterclockwise, it is considered positive. But notice that assuming I will now start to move in a different order that is going back this way, I see that it's going against that our normal rotation of angle. So we say clockwise means negative in angular motion. So if I know that, I don't normally teach this because of the fact that I know that if we do anything we have equals to no need to put this sign, and it's better that way. So you don't have to start confusing ourselves. So in this case, I'll have negative L over 2 and positive L over 2. And in this particular case, what I will have is simply that this particular side of this will not move. It will not cover any distance apart from this point. Why this particular point that you see now, from this end now you just have the L. Are you not seeing it? You have the full length and place. If I'm considering this end now, it's moving through one end. Now notice the whole distance from this. Is it not the distance of the bar?
Yeah.
Sherry? Yes. So this is not divided. So in a case where they are telling you that it is passing through one end, that means that what you are just considering when you are integrating, because this thing you see here, in integral, you have what we call the definite integral and indefinite integral. And definite integral is simply where you have to put plus in constant. While in indefinite, you have to have range of values from this to this. So whenever you are passing through a center, you will not have that this is going to be from L over 2 to negative L over 2. But if it is passing through one end, you will not have the range that is from indefinite integral to be from L, from 0, to L. Are you seeing it? Yes. But when it's passing through this, you will not consider moving from negative to positive. While when it is just from one end, you have to consider moving from 0 to L. Notice that I'm the one that put this in here. You can put your own this side. But the way you're checking is moving from 0 then applying the whole length. So these are two cases that you must consider whenever you're doing this. So far as you know this equation, what you should be checking is, am I putting it in the center? Am I putting it at the end? Once it's at the end, I'm using 0 to L. If it's at the center, I'm using the negative part and the positive part. And that L is being divided into 2. So if I know this, that means that I will now have the integral to the center and saying that I will have I. So the equals to B. I'm still bringing this out one side. So I've already integrated. The minute I integrate, I don't even have to put this. What I just have to put is a boundary, which is I like this. Yes. I've already integrated. Now when I did 2 plus 1 over 3, I see it. I'm not supposed to come and put this integral again. What I'm supposed to put at this point, and I integrated R with respect to R. Because I cannot have R here and I come and have Z here. It's not possible. I cannot integrate R with respect to Z. It must be R with respect to R. That is why you normally see the X over the T or the X over the Y, which means that what you will have there when you are doing the X over the Y will simply be values of X or values of T. It must be the 2. But once it's not the 2, it's not possible to be doing the X over the Z when you have any other variable there. What is not confusing? See, you know why it's speaking that way? It's because you don't calculus, differentiation, and integration. That's the reason. But see what I'm saying is that for the fact that I do this thing from L to R, is because I know that we are using our moment of inertia to be R squared. Assuming it's L, I'll use L because I must integrate or differentiate with respect to the variable that is here. So for that reason, the minute I integrated this, see how we can start this. See, I'm not going to see if I have, for example, integral of x dx. Watch, let's start with this basics. Integral of x dx is simply going to be x. Can you hear me? Are you here?
Yes.
Integral of x with respect to x is simply going to be write out x. Now see what you do for me. This x has a power, see not me, which is 1, right? Come and put 1 here. Then add 1 to it, I'll have plus 1. Is it not good? Divide with the new power, which is 2. This is the integral. Notice that I just brought out the x because it's with respect to x. Is it not good? Now let's say I have integral dx. What you might be considering is simple. If there's any integral dx, it means that this is set as a 1 times x. 1 with respect to x. I know that anything times x is anything times 1 is that is not good. So the integral of this will simply be just x. I see it. Yes. So if you pay attention to these two principles now, it will make more sense to you. So what it means is that if I have just x, I'll be saying, okay, with respect to x, then what am I comparing to it? Nothing is there but 1. I'm going to have x. But if I have x, because I know I cannot come and have, for example, z here. That is doing integral of z with respect to x. I saying it. So this thing now will not work. It's not going to be possible. So if I have, for example, any other value given to me at this point, I will notice that once they are giving me these things that it will be carrying will be having x. That's why we try to do all those things to have time, because we know that there is an equation that already has time inside it. So if that be the case, we can now confidently say that this thing should have come here when I did the arrow integral. Just come and do. Then I have my L and I have my 0. So what it simply means is that notice since I have this now to be from 0 to the length, and remember we are calling it R. You know, remember we are calling it R. We are calling this R because of moment of inertia. I can actually come here and replace this with R instead of L, so that we don't get confused. So what it means is that you know that anything that is this will not be presented as a moment of inertia. I bring my P, then put R raised to power. When it's raised to power 3, okay, I have divided by 3. Let's say I pull out this division of 3 to this side. I have division of 3, then just my R3. Hope you know that by the time I times these two things, it's the same thing. Is it not true? P R cube over 3. If I do P over 3 R cube, it's the same thing. Is it not the same thing? It is. So let me just do my R cube. So I will say when the R is raised to power 3 minus when the R is raised to power of 0. I see it. Yes. I'm doing it out in such a way that what this thing means is that it is moving from going from R being raised to power of R, or let me use my L so that we see the difference. See, what this thing means is that let's do it this way. I'm replacing, as I've integrated this now, I'm going to replace this R. When I see R now, replace it with the L. Let's do it that way so that it's not confusing. Anyway, I see R now, replace it with L. And anyway, when I finish with that, anyway, I see R again, replace it with 0. So that this now becomes, I'll have L. It's just about then minus, that is, this means 0 from L from minus, I'll go again, 0 raised to power 10. And I know that 0 raised to anything is what? 0 raised to anything is what? 0. And this thing minus 0 is this thing. It's not confusing, so that when I have the moment of inertia is simply P over 3. Then I have L raised to power 10. All this one will get out. So you see that this is what I have. Now I will go back and remember that this thing now that I have here. Can I write it here? Yeah. No, I'm not doing this one. If you understand what you are doing, it will be easier for you if you don't remember this. Just remember the equation, which is that our I raised to power 3 over 3. Then the boundary. You remember the boundary. Is it moving from the center or is it moving from one end to the other? So when I have that this is the same thing saying inertia is equal to B L raised to power 3 all over 3. This is my final answer, but I'll remember that this P stands for something. This P is density should be. So I will say the moment of inertia is equal to density is M over L. Is it not true? But remember we changed it to R at that time, should we? And since we have L here, let's look at that. But if you want to change it to R, you change this one to R as well. And remember the reason why we use this one is so that you see that we are replacing the R with something. And then what we are doing for 0. So this is going to now be L raised to power 10 for this one. Then notice that we have our over 3 coming down. This is everything here is our P. And P is times, this thing is the same as saying, when I was there, I can say P times L3 over 3. Then So you see that by the time you have this can easily say cancel, cancel, shall we? So I have 2. So our moment of inertia is equals to m L is equal to 2, sorry, yes, over 3, shall we? Yes. So that is why you see in some cases, instead of leaving it this way, this is your final answer. But you see some textbooks, just the way you do with your equations of motion, they come at 1 over 3. ML squared. This is what they're trying to do there. It's the same thing. It's the same thing. So once, if you can't remember all those integration because we've not done integration, what you just need to learn is simply that moment of inertia, the formula for finding is once the term is at the end or at the center is simply using r raised to the power 3 all over 3. Then the boundary. And this boundary is not going through. Is it going through the center? If it's going through the center, you have going through the negative part. It's divided into 2. So you have, sorry, L over 2. Then you have the negative part minus L over 2. If it's going through one end, you know that it's going to be 0 and the full length. So in that case, it will be R raised to the power 3 over 3. Then the boundary, L and 0. What about the B? The B, yes, and our B, thank you. Our B, I know that B is for density, Shemi. Thank you. And that is when you are doing now, you remember that your B is the same as mass over length. That is, and that length is for volume, and the volume here is for one-dimensional objects. What is making sense? If you don't remember how to integrate, just remember this formula. Then remember that what you now be checking is the orientation. Is it moving through the center? Is it moving through one end? If it's through one end, 0 and the length. If it's through the center, into 2. The length into 2. On the negative side and the positive side. That's it. So, did they give us anything for mass here? And that was okay, just the expression. That is how you get it. And if you even get to the point of solving this thing, something is well.
Space no day
Okay, space no day. Yes. But do you know one good thing about you learning it? It's not every time they ask you just this one. But you know that there are so many objects. Do you know? It's not only one bar we have. We have so many objects. We can have a sphere. We can have circular disc. We can have a lot of things. So that is why I could have easily said, let me come and give you this formula. But it is important to understand this. But it is hard for you to comprehend. Get this formula. If you get it, then get this thing that I just said. We are giving the next question. I want to do it. So that's the answer now. This is the expression. This is the expression. This is the expression. Can I come in?
No.
Okay, see what I did here. I said, Shamir, what I said is simply the integral that I did, is telling me the range of values. Yes, so it's telling me that I'm supposed to move at this point, as I'm doing this now, I'm supposed to move from, since it's moving through one part, I'll say the full length and the end, 0 part. I know that by the time we do that 0 part, it will be 0, and then I guess the full length. So I'll say integral of from the end to the full length, which is 0 and L. So by the time you do it, what this thing means is you integrate this out with respect to the length and integrate it with respect to the end point. So what it means is that I will now be doing integrate one side from, that's what it means. Because you know what displacement is now? When you go from an end to another end, if you want to get what you got, you simply check the final and initial. Subtracting it. So that's what we have now. So what we did here is simply say integrating it out and replace it with when we have end, the full length. Then raise it to that power, which is that time that we have here. Then do the same thing for the 0 one.
Yes.
No, it's simple. If you go to why you can see this is just because you've not learned integration. You need to learn integration is not hard. And that's the problem. That's the problem. Because most of the time they believe that you did further maths instead of this school. So see what you do. See what you do. You know how to make this thing enter you. When you go, today I'll post on the group. I'll post the video on the group on integration and differentiation. There's the mathematics videos that I'll post today on integration and differentiation. By the time you study those video, you see that if you come back to what we did here, especially starting points, it's not stressful, it's not hard. So the only thing that is making it hard is because of the integral. But once you remember this one, I think the next question. He said, come again. D square y. Yes, I know all of you. I've seen it. Okay. Guys, for one dimension. For one dimensional object. Okay, see here. I've seen a number of you writing simple harmonic motion and simple pendulum for this. It's not far from the answer, but we need to be like properly directed. This equation stands for the acceleration of the simple harmonic motion. Yes. Now notice something. This is y, Shebi. Is this not y? Yeah. And y means displacement. If you don't use x, you can use y. X for this side, y for this side. Are you seeing it? Now, at what point, do you remember when I taught you derivative? I told you that in derivative, that when I want to move from, for example, from displacement, let's say DC, I have velocity equal to change in s over change in time. Is it not true? Which means that velocity is actually the first derivative of distance. Shall now let's start replacing this now with y. Yes, and for displacement on vertical axis, because that's what I'm seeing here, vertical axis. Now, and I'm seeing here this. Now let's say I know that, please pay attention. Let's say again I know that A is equal to change in V over change in T. Is it not true? Which means this is the first derivative of velocity. Is it not true? Now notice, this might be simply means that inside this, I have something that is actually this. Is it not true? Which means that acceleration is actually the second derivative of y with respect to t. I'm using this to show you 2 times. You remember that time I said if you are moving from speed to velocity to acceleration. Should we use the remember this? What did I say? I said you differentiate differentiate first, so then get you differentiate. So you notice that this is telling you this way, that is differentiating this y in displacement 2 times. So this is not just simple harmonic equation, rather the acceleration, simple harmonic equation for acceleration of the simple pendulum or the simple harmonic motion. So if it is for the velocity to just be just the y, are you seeing it? Then I'm going to have this way. And notice that this is looking like something we did in circular motion. That time we did w square y, linear acceleration. This is remember? So assuming it's for the velocity, this one will just be like this. Like this. Just like this. For the velocity. Wow. Are you seeing it? Yes. So please, when you write that, write it is the equation for the acceleration of the simple harmonic motion. That's the right answer. Not just simple harmonic motion. Alright. Okay.
Yes,
right.
So we made the first piece and explain the concept of smaller motion. So there's where the government and that was that this is definition of simple harmonic motion.
Yes. Yes, see, he said it's simple harmonic motion. Now see, yes.
That's all for market.
Yes, he said it's simple harmonic motion. It's not wrong. But I'm not telling you what it properly is. This is, we'll prove it now so that you see it. See, for simple harmonic motion, see, do you remember that every motion that we've done so far has the distance part, the velocity part, and the acceleration part, right? Yes. So for this particular equation, if you are calling it well, it is the acceleration, the equation for the acceleration of a simple harmonic motion. Now see how it is derived. See, let me come to this. Notice that, for example, we know that simple harmonic motion is that type of motion. Pay attention, let's see now, we're going to be fast. If we have this, and we have something of this nature, let's say this is the pendulum. Let's say this is the fixed point. Notice that this thing will always go this way. You see that to then come back. So this point is the point of force. It is always having a restoring force. It wants to come back, then go again. Which means that it goes this way. When it goes this way, it is moving against this force. Notice it is going this way in this case. Then when it's coming this way, the displacement is going this way. You see how to different directions, but the force is in this direction. So for that reason, we have that it's having minus x. Now, using one axis to judge this, we say that it has a proportionality constant which is equal to the displacement, but in different directions. So we say that f is equal to minus x. And when we introduce the proportionality constant, f is directly proportional to the displacement, but in the negative direction, the different direction. When we introduce the proportionality constant, this becomes equals to f is equal to minus 3x. I say it? Yes. So on the part, notice that f is equal to ma. Is it not true? Then equals to minus 3x. So notice that if I choose to take a to the other side, if I choose to take a to the other side, this is going to be such as saying divided by a divided by a. This cancel this. So if I choose to make a sort of form is m, I'm taking. So I'm taking m. See that this will cancel this. It's not. Sorry, I have my n. So notice that this my a I'm having here is now going to be a is equal to minus kx. Right? Yes, all over n. So if I now choose to remember that a is the second derivative of x, I will now have, I want to print. So I'm now going to be having, instead of calling it a, I'm now going to be having the square x all over the square t is equal to. Yes, now remember that whatever we are doing is always been changing this over changing time. Is it not good? Yes, now see, I'm replacing, is this true? What we have here is acceleration now. What we have here is acceleration. Because I'm not saying acceleration is v over dt. That is for first derivative. Now for x, it's going to be the square x. Then the square t is equal to minus k. Now we have x over n. So this is another way to put it. So automatically you can see that everything about velocity here, acceleration, has to do with the square. And what is it facing? It is facing our constant and x over n. So assuming this velocity of the it will just be dx over dt is equal to minus kx over n. Yes, assuming this velocity. So it's very simple. So for just the displacement, I'll have it as just this f equals to minus kx. See, it is now when you are not talking about rotational motion and you say that this k is equal to w. When you're not talking about rotation, like it's going around. It's going around. Calm down. That is when you say that this k is equal to w. And remember that w when we started, that w is equal to 2 pi over t. We did this yesterday.
Okay, sir. So you just say that
Yes, It's no longer calling it acceleration. How do you make this side and this side? Because in simple pendulum, when it comes to this point, see, when it comes to this point, there's a point of equilibrium. And when it gets to this point, there's amplitude. This is equilibrium. Yes. So for that reason, since I have x this way, which is constant, with a constant, how do I make this side to be an x? And the only way to do it is to now remember that acceleration is the second derivative of displacement. So that is why we need it to be that way. And then when you're thinking about the rotational motion, you remember all the things we said about the motion. So that particular formula is an equation for the acceleration of simple harmonic motion. Alright, so perhaps. I can't remember what you said. The spring, that one is 2 pi root m over k. T is equals to 2 pi root m over k. That one is for spring. When it's going this way, spring. Yes, that's it. That's the formula for spring. That period for simple pendulum. That period for spring. That is going to be, that's the T equals to 2 pi root m over k. While the simple pendulum is going to be our 2 pi root m over k. Alright, so please let's go to the next one. Shelly, before you learn it tonight to be fun, we'll try saying you want to go. Give me the next question. Please, we want to do this thing fast so that we can start doing our at the end of the swing, please pay attention. That's where. Now please pay attention. Notice something. This is why we call this tutorial. It's instant tutorial you derive the reason for anything you see. Yes, so when you say the simple harmonic motion, it's not wrong. But we need to know what it belongs to. It's just like you may be telling me something is a question for kinetic motion, or kinematics, or straight line motion. It's okay, but it's not complete. We need to tell ourselves, is it for displacement, is it for this? So that's what we pointed out. Now let's look at this question. They said a pendulum, this is 5.6. So they say pendulum has a period of 6 seconds. So let's bring up our parameters. I have t to be equals to 6 seconds. 6 seconds. Then I have my amplitude 8 cm. And I know that cm is not our unit. It's supposed to be meter. Right? So I have 0.0. Then they're not asking me to calculate velocity and acceleration. Alright, let's check something. And notice that the key thing here is at the end of the swing. This is the key point here. The key point is at the end of the swing. There can be a question where they ask us at the point of the equilibrium. Or they can ask us at the 2 centimeter mark. I see it. So that is the key point. So let's analyze this now using our simple pendulum. If I have this to be my simple pendulum swinging, at this point, when it goes to the end, notice that there will be no movement. Is it not true? At this point, it will stop, then go again. Is it not true? Yes. So at the end point here, so which means that automatically, anytime they ask you to calculate velocity at the end, your answer should be 0. No, we will do it together, but we'll see why. But automatically, once they get at the end of the swing, your answer should be 0. Why did they ask you at the middle here? At the middle here is the point of equilibrium. So we'll see why it's going to be that way. Somebody call on what's the problem? Okay, let's now solve. Let's now solve. So I will now say our equation yesterday, whenever we are dealing with velocity, do you remember that there's an equation given to us which is V equals to WR. Do you still remember? Yes. This equation is what you now expand. This equation is what you now expand. Don't worry. Now you now see that this is now V is equals to attention. This is now V equals to W, but instead of R now, you are now having what has displacement here? You are having, if it's going this way, going this way, shall we? Yes. So when it gets to this highest point, we know that it's amplitude. Then as you move this way, what is causing is displacement. These are the two things that are needed. So that means that this is going to, instead of R here is actually equals to my amplitude minus that displacement. I can use X, I can use Y, I can even use R. X. Now, we will not square it. Somebody wants to ask me why am I squaring it? It's going this way. I see it coming to this authority plus 1, going this way 2. What is making sense? Yes. Now, if that be the case, that is why I'm replacing R with this. So it's still from that rotational motion that you get the velocity case. So this is now going to be V is equals to. Now we know that W, if you remember yesterday, we said that anytime we want to find W, that the minute we come and do that revolution, if you are giving a revolution, if you come and do 2 pi times that thing we are trying to convert, automatically we are having our W. The unit is the V. Yes, when we get to question like that, you see. So for that reason, this W is the same as saying 2 pi over T. Do you know why? Because of the fact that we know that this is going to be revolution second. Do you remember that that's what I'm going to say? So the against this will come and put R. Yes, that's our constant R. Notice that it's already having the R over. This is something. For us. Yes, it's equal to 2 So see, why is it 2 pi F? That is our frequency normally. See, frequency naturally is revolution per second. I see it. So if I put it together, this is frequency. Then converting this frequency is going to be 2 pi is equal to 5. Is it not? So by the time you put it together, this thing gives you W as well. So there are so many ways to get it. You are not wrong. So if that indicates this is now going to be roots. Now my amplitude here at this highest point is 8, 0.08. Is it not? Yes. Now, what is my X at this highest point? No. At this highest point, my displacement at this highest point will be equal to the amplitude. I see it. It will be equal to the amplitude. Displacement is equal to the amplitude at the end of the highest point. Why at the middle, at the point of restoration, this point, displacement is equal to 0. This point, notice that if you come here, it is not moving, it's not giving space, sorry. It's not giving space, that is what displacement is. So here is 0. Why at this point, at the end of the swing, displacement is equal to amplitude. Why at the middle, or at the point of equilibrium, amplitude, sorry, displacement is equal to 0. You need to know that. So for that reason, I will now say amplitude minus, which is 0.08 minus 0.08. So 0.08 square minus 0.08 square. I remember that we'll still do simple harmonic motion. So by the time you do it, you see that everything you have here, this minus this will be 0. Is it not good? Yeah. So you have 0. I know that 2 pi over T, no matter what it is, if you times 0, it will give you what? So it is 0. And that is to prove that at this point, there is no velocity. And velocity means movement. There is no movement at that point. So you need to know that. But as we said at the middle, as we said, what is velocity at the middle? What you will now be checking is no longer x equal to a. Rather, it will now be at this point x will be equal to 0. What will the value of the now be? 0.08 square minus 0. Take the square root and 0 square, you get out. Minus it, so we just use this. By the time we square this, see this we cancel this, is it not? Then use 2 pi over T and times this thing. That's the answer. Actually, it's at the point of equilibrium, which is this. Assuming the displacement is here, It's not confusing. See what we saw. This is our answer. Velocity is equal to 0 meter per second. Yes, yes. Our velocity is 0 meter per second. But actually, I'm not giving you an instance. If we are asked to calculate velocity and acceleration at the middle or at the point of equilibrium, at this point there will be no displacement. So that point, our man said that this my r, which is amplitude minus x squared root, will now be set as saying in that case, when I have v equals to w squared, then amplitude is 0.08 squared. And that equilibrium point will have zero. It's not going to be moving. So by the time we do 0 squared, whatever you see that this minus this 0 will not make any cuts. So we simply have square root 0.08 squared. This and this will cancel. So that I have v is equal to whatever you have for w, which is 2 pi over t, then times 0.08. That will be your answer. Yes, the velocity. So what we just do is just put it to the 6. I see it. Yes. Alright, so please let's find the acceleration. Now to find the acceleration is simply still from that our equation. Here. No matter what you do to this thing, even if you put 6 in it, it will still be 0. So see, assuming we are finding acceleration, remember that from yesterday's class we said that acceleration is equal to w squared r. Shall we? In this case now, I will remove my r and replace it with either x or y. I say it? Yes. Somebody said y. Is that what you said? Yes. Why I'm removing this now is for my displacement now. The displacement. What if I replace it with what? Which one? Now see something. Notice that from this formula, which is w squared x, since amplitude is also measure the data. If you replace it, but you just notice that what is determining what we are doing here is actually the movement and the change in that movement, change in position. So that is what we are taking note of when it's acceleration. The change in velocity. That is what we are taking note of. So as it is moving now, we pass the level of comparing amplitude and displacement. Comparing amplitude and displacement is the job of velocity. Are you seeing it? So at this point now, what we are now checking is how the product of the velocity, the angular velocity and the displacement. That's what we are checking. So each one has this stage. So that means that my A will simply be equal to, what did I get for my W squared? 2 pi over 6 squared. Should we? And then at the end of the swing, it's not 0, we got 0.08. So we got 0.08. You are here for me. Whatever you get is your answer. Yeah, that is what you get. Please, if you are understanding what we are doing, what you just need to do is to go home and revise and become part of it. But whatever we are giving you here is how it should be. It's just that you are reading it for the first time. But if you do it over and over, it becomes very simple. And I will still post the video to our group. The problem is that some of you don't even watch the video. You are saving data. Some people, they are saving data for WhatsApp. What data they buy? See, the data they bought in September is still available now. Yes. Someone says, you must see some people. They will be trying to change the code to run it over. That's what they are saying. Okay. So what do you get after everything? 0.07 like this. Should we did everything for me? So I have meter per second square. Remember that I'm using meter per second square peacefully. Using meter per second. Anytime I'm using any equation that looks like this, if you remember when we started, all those linear converting linear to the angular parts. We are always going to be on our meter per second and the rest, not Maya, give me the next one. Can I click?
Yes.
Yes, you guys doing well. Please, if you don't subscribe to the YouTube channel, and you can subscribe. Even as much as we don't remember to tell you to go and follow the channel or subscribe. But I just believe that if it's useful, you find it useful, you not subscribe. So try and be using it, then you subscribe. So that even, I believe, see, there's no number of you don't know. But the way we are structuring things is that even when you're in 200 level, especially those of you that will be in our we have departmental courses that you do for you. Things like your differentiation, then things like your pharmacology courses, yes, and your biochemistry. So have that in mind. So when you subscribe to all those channels, you see that the many videos are posted. No one needs to come and hear them. Just go ahead and use it. I read the next one.
From first principle.
Okay, from first principle.
Of universal gravitational constant.
Okay, from first principle, I should be right dimension of equation. Wow.
And then try to answer the
Is this one not simple?
Yes.
Should be simple? Yes. You can do it now. Yes. Because you know that F is equal to G M squared. Okay, no, you will do it now, right? Yes. From here, make G solid of the formula. Then get the U. So please, let's go to the next one. I think the next one. See, F equals to G M squared over R squared. But if I want to make this other formula, I'll say F. Okay, I thought you said you don't. No, it's simply, no, see, what they are trying to tell you is that that particular gravitational constant, like us considering the fact that everything here, that our G, we are maintaining it to be positive. So we are just going to solve the normal way we do this. But as we are checking if it's downward or upward, we are using negative to solve it.
F is equal to G M1 M2 over R squared. Where B is universal gravitational constant, M1 M2 and R is distance apart. You know in physics, surface of mathematical expression was given by
Is it not true? Yes. And I believe you have the story. Is it not true? You don't have the story. Okay, the story we have is that the way Albert Einstein is known for, or should I say, known to be the greatest scientist of the 19th century. For Albert Einstein, he is known to be the father of physics. Most people consider him the father of physics. That is one. And there are news or cases that even the calculus that we do is the one that invented it. Yes, no, I said yes. And good number of cases we hear that towards the end part of his life that he started acting abnormal because most of the chemicals and the rest touched his brain. Yes. So that's the story we have about it. So you can do your own research. So you don't know about it. Okay, he did it. Alright, give me the next one. What's the next one now?
38.
The slope of a displacement time graph. Is it displacement or velocity? But there's no use. You know that another name for slope is gradient, should be? Yes. So gradient of the displacement. Is it not velocity? Maybe it's velocity. Let's prove it. Let's show how it is. See, let's say I have this side. Look at it. Please keep quiet. This side will be my displacement, S. This side will be my T. If that be the case, notice that if I have my line of best fit to be this way, if I want to draw my slope, is it not something like this? Yes. Now notice that everything I have here, what we need graphical representation of acceleration and the rest. Notice that this is going to mean that velocity is increasing or decreasing. Are you not seeing it? So you see that it is still showing you that arrow, it moves then if it's constant, it's going to be this way. While if it's decelerating, it's going to be this way. So the same thing with when we did velocity. It's velocity time graph. Notice that what we have is acceleration. And remember we said that acceleration moves this way. Yes. So when we are talking about displacement and time, it is velocity here that is changing or that is being created. So that means that the slope we have here is simply velocity. Very simple. And give me the next one.
A train moving with a velocity of 72k.
That's 39.
Play out.
A train moving, yes.
A train moving with a velocity of 72 kilometers per hour.
The velocity
72 kilometers per hour.
kilometer per hour. Okay, I can write it this way. Shall
Yeah. It's brought to rest by
It's brought to rest. Please, what's the right supposed to be copying fast so that we can do it? Okay? What's the rest by?
applying brake in 5 seconds.
Applying brake in 5 seconds.
Calculating the radiation.
Calculate the retardation and distance covered.
Drive during the period.
And distance covered. Set in there. During the period, did they give us any time?
Yeah, 5 seconds.
Okay, during T equals to 5 seconds. Is that all? Wait. No, what I'm asking you there, they said during the period of 5 seconds, you mean?
No, that's during the period.
Okay, so the during the period, sorry. Okay, during during the period. Now, during the period, I'm using T for my period. You are seeing, I am moving. Remember when I talked to mathematics, I said if they say the body is moving, initial velocity is what? No. So see, if they know your body is moving, it means that velocity given is big. Yes, but if they tell your body starts from rest, initial velocity is what? If they tell your body is stationary, initial velocity is what? Yes, if they tell your body is brought to rest, initial velocity is what? So what will be the initial velocity? The body is thrown off, what will be the initial velocity? The body is thrown off, what will be the initial velocity? The body is thrown down, what will be the initial velocity? Because it has gone up and now coming down. Alright, so with that said, we can solve this. So we say solution. Our U will be equal to 72 kilometers. For this, if I can use my so that I don't have to say, I just say times. We know that when 1 kilometer is equal to 1,000. Correct. Times. We know that 1 hour is equal to 3,000. Very sharp. So you see, I've placed it in a way that hour can cancel hour. Kilometer can cancel kilometer. Is it not true? This can cancel 2 zeros. I have punched from the 1 meter. B equals to 20 meters per second. I have then brought to rest. That means that B is equal to 0 meters per second. Then T is equal to yes. When they now ask us to find the retardation, is it not true? So what they're asking us to find is negative A. They're telling us to find negative A. Yes, and the distance. So what we do is, we need to talk about acceleration, we know that we're going to equation of motion. So let's check because yes. But notice that this one will be minus. So now 0 equals to 20 minus. And I can find as a number 0 equals 20 minus 5. This one can also. So divide both sides by 5. So let's See, remember, see. You know the thing to calculate the retardation. Is it not true? That's what they asked us to find. Now we should calculate the retardation. And that means that if we are calculating retardation, we are no longer going to be using acceleration because this thing is acceleration. I see it? Yes. We are not going to be using acceleration. So that is what we use minus acceleration. So we are correct. So we use minus A because what we are looking for is not acceleration but retardation. So we are not wrong. In as much as the answer gave us a positive value, we are not wrong. Alright, now they asked us to find distance, really? Yeah. So to find distance, you know that there is an equation which is S ut. Yes. Somebody wants to ask me, sir, why didn't you use V squared equals to U squared plus 2AS? Is it can before? Is that right? Someone wants to ask me V squared equals to U squared plus 2AS. Notice that this time is important. Please, when you come from class, here. And that one easy to be right. Please, we know that yes, when we started this equations of motion, we gave you 4 equations. But think that that one that has average velocity times time, we normally use it to derive equations of motion. So we have basically 3 other equations of motion that always work. So my S now will simply be equals to initial velocity is 20. Okay? My time is 5 plus half. Now my A is what? Then my T is what? 25. Okay, sorry, 5 squared. So what behind for me? Please, notice that this. Do you know some people's problem? Okay, everything, what is it you want? S equals to 150. No. Do everything for me, give me an answer. You see these academics, we must do it. Yes, we must do it in Jesus' name. Please, how many of you wake up? How many of you wake up less than around 2:30 to read at night? You wake up okay? You wake up around 3-4 to read. Let me see around 3-4. Okay, Puma, you stay up till let's say 1 before you go to bed. Let me see. See, let me tell you. Shabi, you see, once they say medical student, some people are moving with pride. It's not with mouth. That's staying away to read has to be there. It must be there. Like you will not see any of those your medical seniors. They ask them, how do you read? They'll tell you they don't stay awake. It must be there. It's must. If you check yourself, you cannot stay awake. You quickly change the balance before frustration sets in. There's frustration. Yes,
this question here, what is retardation?
Yes.
So retardation is negative.
Yes.
Negative acceleration.
Yes.
But I don't know.
See where you should do it. You cannot use acceleration to find retardation in this case. In this case, what you say is, what is retardation? What does it mean to say something is retarded? It's minus h. Yes. So in this case, when they are asking us for retardation, I'll go to the equation of motion. Instead of acceleration, I'll make it to retardation by putting minus. And that's all we do. And when we finish, he gave us a value that is positive. It doesn't mean that. So you don't put minus. See here. You know, organism, look at us in a food. See there, it doesn't mean that if I get this to become A and I have 4, that is wrong. It's not. What happened is simply arithmetics. Casting out. So in that case, the retardation we are giving to find, that is minus A. And the time you equate this to cross, it simply means that the value we are giving for the initial velocity. See, the value we are giving for the initial velocity here, notice that at this point, we already have V to be 0, which means that yes, for sure it's coming to rest. So if it's for sure it's coming to rest, that's why we have positive. But assuming we have a value for V here, let's say we have a value for V here. You see that by the time we finish this, we'll end up getting that retardation to the negative. So that's what happens. So whichever way you check on please, let's not do manipulation. This is supposed to be negative. Okay. Is that it? Yeah. Nobody's saying that. They ask you to find the distance. Sherry, they ask you to find the distance covered. Is it not? Yes, the distance covered now. These are our formula for distance covered. There's nothing like the retardation distance. Please. Hope you know, hope you know that at the point of retardation, hope you know that at the point of retardation, let's draw something because all these people's guesswork is getting too much. Everybody wants to imagine something. Let's do something here. I want to go if I have this part to be velocity, have this side to be time, V, notice that please watch, pay attention so you see something. This thing, V and time, it will move for acceleration. Constant speed this way. Constant speed this way. Is it not true? Then retardation this way. I see that at the point of retardation, everything here, if you check it, is on the V. Is it not true? And at this point, as it's coming to rest from this now, you see that the velocity to have is this velocity from this end to this end. Because if you check it, there will be a time, the velocity on this end. So which means that what we are actually checking, if it's retarded, is not distance. What we are checking is velocity. And from the question they gave us that the velocity there is 0. So I'm not having any business to do with when I want to find my distance. I will come and start putting my A to the minus. I don't have business with that. I ask.
What do you use B squared equals B squared plus 2AX?
Which we said we can't use because there's time. In any of this square plus B square plus 2AX, there's no time there. And the time is important because we need to take note of at what time did they do that time. Assuming we got acceleration to negative, that means that is retardation. Even if I put minus A here and I carry it to put here, it's still retardation. I see it, so I'll use what I have. Because see, let's say I have my minus A. I'll make a solid of the formula like it will cross over so that you have A equals to minus this. Is it okay? So whatever I have here for my A, whatever I get here, I want to substitute for my A. So it doesn't really change anything. The only thing we need to understand is just this part, this starting part. But please give me the next question.
I'm sorry. Write the examples of vector quantity.
3 examples of vector quantity. You know displacement, you know velocity, you know momentum, you know everything will be treated that is not a scalar quantity.
No,
scalar quantity. Whichever way you want to pronounce it, when I give 41.
An object is acted upon by two forces, 15 Newton and 20 Newton.
But 41, shall we?
Yes.
But let's do it.
Calculate the number of times of the
I don't want one day. See, please. I don't want one day. You see me in hobby. All these things that we've treated when you're in class, you come and tell me, sir, see this question. Please, sir, what's the answer to this question? Good number of you are fond of that. So please, as we're doing this thing now, pay attention. That's why I'm doing it. I am doing it.
an object was acted upon.
This year will soon be carrying care to class because of you. An object, woman,
Is acted upon by two forces.
is acted upon by two forces
Of 15 Newton and 20 Newton.
of 15 meters and
15 Newton. Calculate the resultant of these forces.
calculate the resultant. Is that it?
Of the two forces.
Of the two. We've done something like this before now.
Yes.
On the two forces there?
If the forces act at angle 60 degrees.
Okay. If they
Forces act at angle 60 degrees.
act at angle.
60 degrees.
So please look at this person. Read it again.
Okay, so it's an object affect performed by the forces of 50 Newton and 20 Newton. Calculate the resonance of the two forces. If the forces act at 60 degrees to each other.
Okay. See, what I'm going to be checking there is the angle. Is it an acute angle or obtuse angle? Acute angle. So it's less than 90. So whenever it's less than 90, I told you that there is a force, a formula to use. So if it is equal to 90, if it's equal to 90 translation, if it's equal to 90 degrees, I'll simply use Pythagoras, which is r squared equals to f1 squared plus f2 squared. If it is less than 90, I will simply use, so that I don't stress myself, I'll simply use r squared is equals to f1 squared plus f2 squared plus 2f1 f2 plus theta. When it's less than 90, because this will give me positive value, and I need to maintain the positive value. But if it is greater than 90, which is obtuse, I will use r squared equals to f1 squared plus f2 squared minus 2f1 f2 plus. Now see, I will now do that angle I'm giving is going to be above what's it called? 90. So I'll say cos theta. Do you know what I'm using cos theta? Yes. So if you come here and do 180 minus theta, is in this one we do that thing. That means that this one, actually we want to make minus here, make use of minus here. This one could have been cos 180 minus theta, because we know it's less than 90. See now to that's where we could have done that, so that we can get, by the time you subtract that angle that is less than 90, it will not give you a bigger angle. That will not give you minus, and the minus will cancel this. So simply maintain this formula for it. What you just need to be noticing now is just, if it is above 90, use minus, then put the angle. Just the angle. If it is less than 90, use plus, then put the angle. Then if it is equal to 90, just use this. Very important. So we don't start checking all those things we normally check and you enter all. Okay, so this angle now is 60 degrees shading. Let's use it to solve for the resultant. So let's see which one are we using now? Very simple. So let me clean the others. Let me clean the rest. So the goal is always, now see, we have r squared is equal to f 15 squared, yes, plus 20 squared, okay, 15 times 20 shading, cos 60 degrees. Yes. Reason why we normally do this is that if you happen not to use it this way, at the end of the day, you might go wrong. Because those signs will not make you subtract when you're supposed to add, or add when you're supposed to subtract. So what do for me? Add when I equals to square root of, shall you know, taking the square root of both sides. Or you say do it this way, I say do it this way. So you want do it for me. Then I do the final answer. Let's go forward. But I know this is going to be new to me. So with this formula, we don't need to start stressing out ourselves doing all those work we normally do. Yes, we normally come and do, for example, 60 degrees. Then you come and do 15. So if you finish it here,
So that's the
the formula. All those things we normally do. All those things come and do that usually. So you see, instead of doing this thing now to find r, you have to come and do this is 6 usually. Now check that. Notice that if I project this and start drawing this thing, this particular side is being like this side, it's not corresponding angle. So the second one is like 180 minus 6 will get what? 120 revolutionary. So instead of doing all these things, just use this formula. Okay, that's our x. That is carrying this one to the x, carrying this one to the y.
No, that's not me.
That's it now. Resolving to x, resolving to y. We can do it now.
No, that's what I'm saying. That's what I'm saying. Like, let's say I'm going to say, we're not saying resultant of 15 and 20.
Resultant of 15 and 20. Okay, then you come and take the square root. It's not possible because there's an angle that is not equal to 90. It's not possible. See, that thing you're doing, if it's not what we are taking, that means you want to do magic. Then, we're giving the next question 42.
Both us for me.
No, don't worry. Acceleration. Yes, so see, velocity. Time, we need to be skipping fast on this one. So if I have this now, line of best speed, if I drop my slope, please, there's something I want you to note. Hope you know that anywhere for your slope, hope you know that anywhere that your vertical line meets your x-axis, that becomes your s2.
Wow.
Are you aware? So if, for example, I have a negative graph like this one, for example, I have something like this. And I'm drawing my slope. That's why I normally tell myself to draw the slope like this. Do you know what this means? What it means is that this point is your x2. Some people want to doubt it. See? Why you want to doubt it? See, remember that first of all, when you started your graph, you will first number, is it not true? You will first number now, is it not true? You will number, then number. So if, for example, I have, let's say I have 10 here, and let's say I have 4 here. What I will now have is not going to be that. I will now have y2. Please, that's the noise. That's just minus y1. You are deciding my class. x2 minus x1. This is going to be said as saying whatever y is and whatever y1 is. This one will be 3 minus 4. Please, I'm serious about this. So this is not going to be, see now by the time I just this will give you a negative sign, it's not.
Yes.
So it's very important to note this. Whenever your vertical axis meets your horizontal axis becomes your x2. It's very important to do it. So if, when you are doing this one that is always positive, this one is x2 not because of the values you have, but rather because of the fact that the vertical and the horizontal meet. So if I have a negative slope, if I have a slope like this part will be considered my x2. So you need to know that. Alright, so let's go to no, why is the same? Why is the same? Notice that this is my y and this is part. No problem. No problem. Alright.
So an object is rotating about an axis.
Yeah, this is analyzing it. Our answer is 30 points.
Acceleration.
Okay, velocity time graph. The name can be simply going to be V and T. Now, if I have my line of best speed this way, it simply means that what I have here, notice that this movement gives me the acceleration. Even when we did our graphical representation of velocity, it's going to be always this way for the acceleration, this way for constant speed, this way for acceleration. I want us to do fast because this is not what I really want us to do.
An object is rotating about an angle with your very
40 what? An object
is rotating about an angle of radius 0.4 meters.
about an axis.
Of radius 0.4 meters. 0.4 meters.
Radius.
At a constant angular acceleration. 0.4.
0.4 like this.
Yeah.
Thank you.
At a constant angular acceleration.
At a constant.
Angular acceleration. Let's do number 5.
I can't even remember it. What me and Maka is doing? Constant like you.
Of 0.5 grams per second square. No, acceleration.
It's well. It's well. Let them not just come one day and say they want to carry someone that people are going nuts. So you will not stay in class. People will just be laughing at us. See, solution, let's check something. And the first thing we normally analyze are the parameters. So I have arrow 0.4. Okay. Then the big acceleration
0.5.
Okay, you're used to alpha. Well, see, in this question, because they mentioned acceleration, and the only thing they're asking us to find is radial acceleration. So please, because acceleration was mentioned, we need to first of all this equation of motion to obtain our velocity. Do you remember that radial acceleration is the same as that as linear acceleration? That is A equals to W squared R. What we know? And we said that this thing is the same as V squared over R. This statement because W is V over R squared. Then we have R. So squared. Times this will cancel this. So it's the same as saying V squared over No. Radial acceleration is the same as our linear acceleration, or you say centripetal acceleration, whichever way they want to call it. I am saying, if I know that I will now say W, if you remember from the question of relation, W not equals so W will be equals to our initial velocity is 0. Somebody did not ask me how. Okay, you don't need to ask you already know. Because before I can accelerate, if it's not considered, yes, plus. So, it's not going to talk about but everything is
equal to 2 rads per second.
You know what I like about this? Okay, my friend, I'm sorry. What I like about this story is that you see sometimes when you're in your final year, when you're describing somebody for somebody, you will say, hey, that one, now that time I need a tutorial, now mass communication blog, that one that used to, so somebody like Rita now, when you are describing her for somebody, you easily say, no, I only stay in front seat and read questions, things like that. She quickly punched the I told her something. When we refused, she kept punching till she got our answer and right. So keep punching. You cannot replace AI. Stick the original AI here. So you will do it so I give you an answer. So please, let our answer is not wrong. As if check it and check well, you let them get something that is the center with our own. I am saying. So we're not going to find the radial acceleration by doing okay, you found it?
Yes, do it though. Use this formula replace
okay, A is going to be 2 squared. Okay, 0.4. Is it? Like the 1 point. The other is 1.6. And I know that this is meter per second.
Number 44.
We're doing 44.
What is waste energy? What is waste energy?
What is rest energy? Please, Uba. Yes, the energy of body possesses due to its mass. Yes, it's not even, I won't like to put it as potential energy. It's not potential energy. I won't like to call it potential energy. When you advance in modern physics, this rest energy is simply given by is the work of our chest, that's our MC. Yes. So this is what rest energy possessed by the body due to its mass. And what he's saying is that in as much as you are not working or when you are not doing anything, not that energy is already to do. Like there's an energy you possess, for example, you possess so much of chemical energy. Yes. That is why as a woman being, whether you work or you don't work, if you stay for some time, you will get hungry. And the minute you eat, okay, like yeah. And the minute you eat, you see that what happens is that all of a sudden your body gets normal. That is one. Another energy you possess is actually heat energy. Not as much as your chemical energy, but you possess heat energy. Which is why if you are in a place where you are not supposed to be, automatically, even without doing work, you start sweating. Is it that true? Yes. Yes. So you possess all this energy by virtue of your mass. So we say that rest energy is energy possessed by your body by virtue of this mass, or this mass. Alright, it's given like this. And we know that this one is equal to what? And stairs is equal to what? You stay, remember, the speed of light. Yeah. So you need to know this. I am giving the next one.
A ball is moving with a velocity of 0.5
Okay. Question what now?
45.
God, thank God, remaining just 5. Okay, 45. A body.
A ball is moving with a velocity of 0.5
It's moving with a velocity.
The velocity is decreasing.
Calm down. It's a velocity of
0.5 meters per second.
0.5.
Its velocity is decreasing.
Imagine if we don't have this like this class, so nobody will believe it for us.
Yes, you're right.
At the rate of 0.00. Okay, 2. I'll give Rita a present after today's class. Yes. 0.00. What is what? Shebi, for a class, all of you will just keep quiet. Nobody is participating. Everybody that take this is how all my class will be. Active. I see, let's solve it together. So please, if you notice something, we actually are doing this without even thinking about it. Anytime there's acceleration given to you in an equation of motion, know that if acceleration is given, it's best to first think of how to use equation of motion to solve that question. So once you know it, it will save you the stress of trying to think of all those parameters that come with formulas. So you just use equation of motion to see what you can do with it. Alright, they say one is moving with a velocity, so my u is going to be then they say its velocity is decreasing at a rate. Okay. No, the velocity is decreasing, Sherry?
Yes.
Yes, and they're every meter per second square, right? Yes. So I minus a. Will be 0.005. Then, okay, see, is See, now why I'm using minus 8 because I know that we are talking about decreasing. So if I make this a solid of 4, you see that it will move to this part. So that I have minus. So now I will put this inside the function b equals to u plus ac. Please, it's not about cramming or memorizing equations of motion. It's about whatever you are given in your question, being able to pull it out, and then you now know the equation to use. Because if I'm giving time, I try to use the one that does not have time for one problem. So, and one thing about this equation of motion is that everyone you use will give you an answer. So don't go ahead and shall now be equals to 0.5 plus minus 0.005 and then bracket 4. Now see something. If you remember, please pay attention. If you remember that question we solved the other one, then they talk about the retardation. Is it not true? So nothing that this one we are giving retardation as well. What we just do is to put the minus. So it's the same thing. Us saying we use velocity acceleration and solve, and after solving with acceleration, you now come and put minus to the value. Is wrong. So that is why we are putting this. When I want from you what we are.
0.4.
That is for everything.
Yeah.
So 0 point. It's going to have minus, right? See now, see. So we have minus here. Okay, by the time you do this, it's less than this. Okay, so you now got 0 0.4. Many good. Do your own. Punch your own. Why is it like this? This one, the question said is decreasing. The question said decreasing. So when we hear decreasing, and they give us that this is measured per second, that means instead of acceleration, it now means retardation. So that's why we put minus. I have question 46 now, right? Yeah. We are giving the question.
Why is that the Earth's gravitational potential is always
I like that. Why is it that you know some people are saying it's a lie, we will not give them something. You're playing. Why is it that the Earth is always negative? Once you finish, read the first. I know my physics students too. And the guy on glasses. I have someone should give me the answer to this one. I know we give it to the last class. Because it's fighting that was Shelley. Yes. So yes, we said in our last class that the gravitation of the Earth is downwards. That is everybody that is going up. Notice that naturally the body is going up is coming down on this own. You are not the one doing the work. So for the fact that it's always telling or pulling it down, we say that it is a negative, it is having a negative value. That does not mean that, yes, negative, because this side, if you notice here, this is our y-axis. This side is positive and this side is negative. Yes. So we normally say that G is in the negative axis or always negative, meaning that it's pointing out. It does not mean that we should not go and put minus 9.8. Because somebody wants to ask me, why is it that it's not, G is not having minus 9.8? No. What we simply mean is that when you are comparing the movement of gravity with the Earth, what happens? It is going towards the negative side, negative vertical axis. That is what we mean. And it has nothing to do with what the value should be. So with what they are asking here, why is it that it's always negative? What they are just trying to tell you is that if you have this and you have this, putting the two and two together is going down with the meaning that is going on the vertical axis. That's just what they want you to prove. Gravitational potential. Remember that gravitational potential that we're talking about is simply attaching potential energy to it. When you hear potential, that is mgh. So the g there is what we're looking at. I see this. If a body is at rest, I am not considering that. Or you say a body at rest. If a body is at rest, even as much as it is on its own, there is a force acting on it that wants it to come down, even when it's not in motion. And that means that the G is what we're looking at. This G is what we're looking at. That's just it. So it is always negative, but it is considered to be always negative because it is going towards the negative vertical axis. It is pointing towards the negative vertical or negative y axis. That gravitational potential you see is just talking about if the body is at rest, there is a force that is acting on it. I even showed it to you when we did this stuff that there is normal force and there is force that acts on that wall, which is mass, which is W, mg. If you remember. So if you are not putting potential here, it means that this is not mgh. That is the distance. So we are just considering the g here, which is the gravitation. Okay, so what formula did you find? Minus gm all over r. Minus gm all over r. Notice that what you're actually giving me. And notice that what you're actually looking at here, what you're doing here is actually pointing force to the first place. This is not your G. That's what I'm saying. Notice that what you're doing here, forget that definition. You pick this from somewhere. Notice that what you're doing here is the same thing with the Newton's law, which is just that this one is not having the square. This one is not having square, and then it's not having R square. So notice that what you're pointing here is still to your force. So when we are considering this, we'll consider the fact of its G, not what you're doing here. So because if you check it, even G that you have here is not on its own. So if you make your G subject of the formula, you see that it's the same thing with what you did here. That this one will not have square. So please, if you are describing this, what you are just giving them is that it's because it points towards the negative vertical axis. That's your answer. That's the answer. They don't say you should give a definition. See, nobody is asking for definition of the formula. What they're asking is why is the gravitational potential always have a negative value? Because it's pointing towards the negative vertical axis. And give me the next one. This question is not that big for us to come and dwell on it. And two forces there. So please, always think of how to make this order of the formula anytime you see it anyway. So for the seven, two
forces whose resultant is 100 Newton.
Whose
Resultant is 100 Newton.
resultant is 100. Okay.
Perpendicular to each other.
Perpendicular. Perpendicular means 90 degrees. What below perpendicular means 90 degrees? Okay, to each other, eh?
If each one of them is an angle of 60 degrees.
Then I say if one of them then they are not asking us to calculate the magnitude. Okay. They're asking us to calculate. Okay, so please remember we normally use this statue as part of our revision class and practical class. So please, yes, I'll show you on practicals. Once you have yes, I know I'm going to correct it. So let's try to look at this, please. Let's see what they are talking about here. Notice we are rushing this one. It's not like those ones will come. We will solve. Explain. Before you know, 4 will now. We will go. So we have fire 47. Two forces, Sherry. Let's go 1. F1. Okay, that means, see, that means they have a force. Let's say this is my F1, which is what? 100. Let's say I have F2, which is another 100. Relax now. Okay, wait, is it the resultant? Yes. Okay, let's say this one is 100 meters, Shelly. Yes. But I don't know this. Yes. And I don't know this, right? Yes. Okay, for me to resolve this one, I'll ask myself, if I have something on this end, and I have something on this end, notice that this is my X as well, Shelly. This is my X as well, and this is my Y. You see that? So if I succeed in pulling this way, let's say this is the 90 degrees, let me bring it up here. No, you open your eyes. Dog, can you have it in a phone? Okay, yes. Malu, let's say this is my 100 meters, Shelly. Okay, now this is the side for the socket. So this is my F1. This is my F2. So what this thing means is that, what are the forces I will have on F2 or what are the forces I will have on F1? Notice that if I pull this thing down to this side, this is also my F2. Okay, no. And this is also my F1. It's supposed to be 90 degrees. Forget the fact that it's not there. So what I will be checking now is ask myself, on the F2, I have when I have a force here. This force now. I have when I have 0. And also, if I choose to resolve this resultant to F2, that is going to y-axis. See now, yes, 60 degrees, Shelly. 60 degrees to each of to the resultant. Let's say this is what 60 degrees. So you see that if I'm putting this thing now towards the y, and F2 now will be F2 sine 60 degrees. Do you still remember? Yes. And notice that it's on the negative part, our vector. So I have minus. Sweet. This is y now, Shelly. Y has no minus. Yes. It's x that has minus. I'll
just give you just do it right now.
Yes, you just bring it in.
Right there for
Don't worry. This, you know that method. You know what that method. That method is because you cram this. When you want to do it in a way that students will understand and be able to remember, this is how to go about it. You have your resultants, you put your quadrants. Now, please. See, if I'm taking this now, on the x-axis, notice that the forces on the x-axis will be this side. Shelly? On this side, I have F this way. So when it's 0, and then when it's going to be carrying this resultant now towards x-axis. Towards x-axis, notice that this is minus x. So I'll have minus F1 cos 60 degrees. So that is how to go about it. So I've been able to pull out all the forces in F1 and all the forces in F2. So what I will now do is to now find their individual magnitudes. So I can now claim this. You say what? I got F1, F2. Yes, see now I have 2 forces given to me. And these 2 forces are totally. Then they tell me that they are perpendicular to each other. Shelly? And they then tell me that there's the resultant which is 100. Then they then ask me that what if one of them make angle 60 degrees with your resultant? So I said, let this be my angle of 60 degrees with your resultant. I said it. Somebody wants to ask me, why didn't you do it here? Yes, there are people that want to ask you that, why didn't you do it here? Now notice something. So I made an angle of 60 degrees with it. So I'm now analyzing it and now put this out. It's not so that if I'm taking this to this part, I'm not taking this to this part. Then initially, if I have this, it should have a 0 and it should have a 0. Then I'm resolving to the x and to the y. So I know that if that be the case, if this is on the horizontal, I'm supposed to be having 60 degrees. That's why I have 60 degrees and I'm resolving it. So if it's on the vertical, I will simply do 60 minus 90. This is, everything here is 90, Shelly. 60 minus 90, that is what is remaining, which is 30. Is it not true? Yes. And you know that if you use 30, still is settled with 60, just that when you are not doing it, to not be, because cos 30 is settled with sin 30. Sin 60, sorry. And sin 60 is the same thing as cos 30, shall we? Yes. So it's best to do it on this way. So now when we finish, we can now resolve. So you have to for me. Remember that force that I'm pulling, remember that the force I'm pulling here, that I'm moving to this part is 100. Is it not true? So I'm having 100. So for F2, I'm having 100. So now do for me 100 cos 60 and 100 sin 60. So please, how I teach? Okay. Here. I have this. I have F2, F1. This one, this thing here is 100. That means there's 100 here. That's now pulling this way. So I purposely wrote F2 initially so you know we are going this way. Alright. 86 points. 86. Okay. 86.60. This is minus 50. Okay. So you see that, and notice that this is going to be in Newton. And this is going to be in Newton. So their individual magnitude is just this. So now how to know if you are correct is that the minute you finish this, notice that we resolve this in what it will be on a particular axis. Let's say x axis, y axis. So we now say if this happens to be r squared equals to roots. That is when you take the roots. We now do that our x squared, which is minus 50 squared. Then plus 86.60 squared. Now I'm going to check if we are going to get 100. I see it. This is how to compare it. You see the way I teach is in a way that we are not here to prove to you if we know something. What we are trying to do is to show you so that by the time you go home and you are thinking of it, you don't have difficulty. Or you are not remembering it like somebody that taught you. And you're not remembering it like somebody that taught you out of cramped experience. No. So this is how you should do. So you don't have that. So R is equal to 100 Newton. That is how you prove it. So this is our answer. This is magnitude. So copy. So number what now? You said you don't understand how 100 was fixed. You are not paying attention. You are not paying attention. Something I did over. See what magnitude means. Another name for magnitude is value. Can you hear me? That is why in your mathematics, when you do absolute value, have you noticed that the sign you use for absolute value is looking like that our vector sign? Do you remember? See? Notice that time we did vector, when we do magnitude, we normally say magnitude of A, for example, come and say A magnitude is equal to whatever is inside square. You still remember? Yes. So anytime you hear magnitude, another name for it is value. So what we are asking you by saying find the magnitude is magnitude of the two forces. That you should find the value of the two forces. And that is what you got here. Find the value of the two forces. That's what you got in there. Okay, and what's the estimate of momentum? From what we've learned in class, what's the unit of momentum? What we've learned in class, what's the unit of? See, all of you in this class, you all need A in physics. I'm telling you the truth. Generally, we are starting from the beginning. But everybody in this class called you A. I am expecting that by your, it's not planned. If you ask yourself, if you see the result of medical science students, it used to be A parallel. You'll be imagining it's a lie, but it's not true. So every one of you call us A's. Yes. So if you notice, however it is we are teaching, once you start asking your question, we'll purposely go back to repeat it because we have time for you to get from A. Now somebody that asked me, you don't understand how I got 100 sign. See, the question said I have two forces perpendicular to each other. One is F1, one is F2. I don't know what it is, but I know that there is 100 here. Is it not true? I can even use that my soccer tool to do it. But I chose not to do it that so at all because I know that what we've done so far so good is vectors. So we now said, if that be the case, that this is the same thing as saying, if I have a y-axis here, and I have an x-axis here, if this is coming this way, this is 100 as well, everything on this. We now say, what are the forces that will be here? Notice that initially this side, I have this on this way, which means it's 0. And then for x, for F2, 0. Then if we now start resolving this particular result, if you go to y-axis, it will now be 100 sine, and there's an angle between you. It will be 100 sine, 60. Then if I carry this now and come to F2, is it? No. And if I carry this now and come to F2, it will now be cos. Coming to x is cos, going to y is sine. So check our vector video, you understand it more. That's why we use vector to resolve it. So after doing it, we have the one. Then we use this to check if our answer is correct. Alright, let's read question 48. I know there's time, so let's do 48 for time. Okay, 48 we've got it now. Momentum is simply mass times volume. Shall we? That's velocity volume. And we know that velocity is bigger than second. So we just say kg. Very simple. I am giving the next question. Is it? Okay, yes, sorry. That's because the first thing, please, whenever you're doing vector, somebody wants to ask me how do I know this side is F1 and F2. The first thing given is for x-axis. The second thing given is for y-axis. That's why I did this. Okay. May I give a question 40? I always think this is good, so I have to visit for me in SI units. Okay, the product of velocity of y is good. Just is times 1 kilometer over 1,000 meters. And times 1 hour for 3,600 hour cancel hour. Should we say? Kilometer cancel. Papa, anyway. 50. 50, the last one. Papa density of. Papa density of 0.10 grams per centimeter. You can see gram, I will do it this way, times 1 kg, that is 1,000 grams. I always put the one that I have in the place where it will cancel. Then times, now, I know that 1 meter is equal to 100 centimeters, is it not true? So which means that 1 meter cube will be equal to 1 million centimeters. Is it not true? And so I'll put 1 million centimeter in a place and describing cube. In a place where there are cancel, so meter cube. So 1 meter cube equals to 1 million centimeters. So centimeter cube cancel centimeter cube. Gram cancel gram. Now by the time you punch it, what do you have? Okay, you're waiting for it. What? Hear this thing! Son of man, hear calculator. This is what does it have? Maybe the one. So, this class, if you cannot come to school, you might have school. Please, hear calculator, what did you get? 100. So, we're getting 100. And notice that what we have left, we need to have that is kilograms. And then meter. I see it. Alright, so please. Yes. So, we really try. We beat time. Alright, let's go to We beat time. Let's start the practical class. Let's start our practical class.